Part 2, extensible data. Let's talk about a few things here. First, we're going to talk about constraint unification, which is the process Elm's compiler uses to type check everything. We'll talk about open versus closed records. Talk about why open records exist. And finally, we're going to talk about extensible custom types. All right, let's start with constraint unification. So the way Elm's compiler works is it basically starts with a series of known facts about type constraints. So here are some examples of those. Stuff is a string literal. It says, okay, I just hard-coded, I know what string literals are. They are all strings. I know what floats are. They look like that. Every time I see that literal, that's a float. Every time I see one of these, that is a list of strings, which it knows because this is a list literal and this is a string literal. It also knows that empty list is a list literal with an unbound type variable, so list of A. So these are things that the compiler just knows. They're hard-coded. It doesn't need to do any type inference to figure them out. It just knows them. So these are the known facts that it starts out with. And then it basically goes through your program and starts inferring new facts. So here's an example of how it might do that. Let's say we have this expression, hi, my name is ++ name ++ exclamation point. So it says, okay, well, this is a string literal, so I know that's a string. Here's another string literal, I know that's a string. ++ combines two strings, so I know that by inference, whatever name is must be a string. So now it's added this to its list of known facts. It says, okay, I have used what's known as constraint unification to say, by virtue of what I already know about these other constraints, this constraint must be a string constraint. That's what the name's type must be. And as it continues going through the code, it keeps doing this. So let's say we have something called working, which is assigned to not is broken. So it says, okay, well, not is a function from bool to bool, which means that since we're passing is broken to not, well, is broken must be a bool. So that's another form of constraint unification. And then because working is assigned to the result of not is broken and not returns a bool, it says, okay, well, working must also be a bool. Then let's say later on in the same let expression, we have caption equals string.toUpper working. Now it says, okay, well, string.toUpper takes a string and returns a string, which means that working must be a string. Uh-oh, we've concluded two facts that are at odds with one another. In one case, it claims that working is a bool. In the other case, it claims working is a string. These are contradictory facts. This is how we get a type mismatch. So as soon as it encounters a contradiction like that, it's like, okay, our constraints have unified to something that does not make sense, therefore type mismatch. Now with parameterized types, it's a little bit trickier than that. It's not as straightforward. So here are two different append functions, string.append and list.append. Both of them do the conceptual operation of squishing two things together. So string.append takes string to string to string, list.append list A to list A to list A. Now if I call string.append on a string and something that's not a string, well, it stands to reason that's going to be a type mismatch because it says, well, these both need to be a string. The second thing you gave me was not a string. But you can't quite extend that same pattern to parameterized types. So here, I'm appending a list of strings to a list of A. Now those are not exactly the same type, but as we all sort of intuitively know, this will still work. It'll give us back A, which is a list of string. So how did it know to do that? I mean, we understand how this works when they are literally different types. But in this case, they still are literally different types. It's just that it figured out, okay, but these are compatible, and it put them together. And not only did it figure out that they're compatible, but it concluded that it could resolve them to a single type, which in this case it decided was going to be list string. How did it decide list string over list A? How does it figure those things out differently than it figures them out with string and float up here? So this is the process of constraint unification in the presence of type parameters. So if you have two types that are exactly the same, including their parameters, they're identical types, okay, then it's going to unify to the same thing because they're identical. There's no unification that needs to happen. If one of them is more constrained than another, for example, list string is more constrained than list with an unbound type, then it says, okay, we're going to go with the more constrained one. We're going to unify to the one that's more constrained of the two. And if they're incompatible, then it says, okay, type mismatch. So let's see an example of this. List.append A, B, and C. These two are identical, so they're going to unify from list string to list string. And it says, okay, those unify to list string. Let's say we do A, B, and empty list. It says, okay, list string, list A. Well, list string is more constrained than list A, so it says, okay, those unify to list string, the more constrained of the two. And if we put two empty lists together, once again, they're identical. So of course, list A to list A, list A, identical. Another constraint we can have is number. So number is a constraint that is somewhere in between an unbound type variable and a concrete variable like int or float. So number is one of Elm's three constrained type variables. So number means this is either an int or a float. The other two constraint type variables are appendable and comparable. So appendable means it's either a string or a list, and comparable means it's a int float. There's a list of these. String, if you ever get a mismatch on like trying to put a non-comparable thing into a dictionary, you'll see that error message. It lists with it. There's like 7 of them. Regardless, they are more constrained than your typical unbound type variable or your concrete parameterized type. But when they're identical, they work out the same way. If we have 1, 2, and 3, so just from this list literal, we know that this is a list of numbers, but Elm, just based on this syntax alone, if we just put this directly into Elm REPL, it doesn't know if these are ints or floats yet. We haven't given it enough information. A literal starts out as a number, and then it might get more specific later depending on how it's used, but at first, it's nothing more than a number. Okay, we can also append a list of number to a list of unbound type variable, and that unifies to number, because number is more constrained than unbound type variable. So although we still have an unbound, we still have a type variable in here, it's not concrete yet. When you unify these two, you do still get something that is more constrained than what you started out with on one side of the expression. Now if you unify a number with a float, now, okay, it says the more constrained of the two is float, so now we unify to float. Okay. We can still get type mismatches when it comes to number. So remember when we did a list of A with list of string, that unified successfully to list of string. The problem is that number is not compatible with string. So even though this is a type variable, it is constrained, and its constraint does not support string, which means that if you try to unify a list string with a list number, you'll get a type mismatch. But list string with list of unbound, totally fine. Questions about that before we move on to records? Mm-hmm.
So I guess for a number, it follows the pattern of like lowercase as a type variable.
Right.
But this is kind of like a built-in Elm thing. That
Yes.
means it's a variable because it can be multiple things, but there is a pre-described meaning to the domain of those variables.
Yes, exactly. So the reason for the syntactic choice of having it look like a type variable is that in all ways it behaves like a type variable except for the extra constraint. So for example, you can choose the name. It just has to start with number. You can put number A, number B, number C if you want to have multiples of them. It gets replaced by a more concrete type, such as float if it's unified with one. So in most ways it behaves like one, except for the additional constraint that it has baked in. Some languages have these, and they have like different syntax for them. So there's a lot of trade-offs in language design, and so the choice here was just to go with looks the same as a type variable, but has some extra properties to it.
So in comparison to if it was a custom type, where you would now have to be able to handle all like adding and.
Yeah. So that. There is conceivably a way you can do that with phantom types, but that's a tangent. There are other possible designs for this, but the important thing is the way that the constraints work out, is that you can have something that represents either an int or a float, and they don't unify with strings, but they do unify with ints and floats, and they unify to the more constrained of the two. But yeah, I mean, there's a whole, you can do a lot of bike shedding around how to do constraints, syntactically or otherwise.